In this video, we're going to investigate how to apply some of the statistical rules and graphical analysis tools we've been studying to a more complex case study. The study that we're looking at is going to be looking at 3 different machines and deciding which one should be replaced out of the 3. And the source for the study is the NIST Engineering Statistics Handbook. And the NIST is the U.S. National Institutes for Standards and Technology. So they are, in many ways, the source of biblical level information about engineering and standards. So what we're going to look at is a quick background of the data, and this is paraphrased in the Python document as well. But the basic idea is that they're trying to determine which of 3 machines should be replaced and how to go about making that kind of decision. The first thing that's crucial is deciding on what basis the decision is going to be made. So here they're looking for characteristics like least stable. So that means, at least one interpretation of that is over time, which of these particular machines is least consistent and has to hit a certain target for the pins that it's generating or producing. And constant variance about a constant mean is how they quantify that stability. If it's determined that all machines are stable, then the decision about which machine to leave off will be based on the process variability and throughput. So I'm going to highlight those as well. So process variability and throughput. So throughput is just how many items, how many pins can be generated by the machine. The machine that's least consistent or has the highest variability and the lowest throughput will be the one replaced at the end of the day. So there's a bit more information in the reading here about how these different characteristics will be quantified and measured. They have an interesting feed here that's beyond the scope of this course, but just recognizing that if you're looking at consistency of the thickness of the pins at the end of the day, all of the various factors that could play a role in that, coming from the machine side, from the material side, how the machine is being used, and also how the measurements are actually taken. So measuring the thickness is not without error in itself. And the result of their analysis of this whole process was that many of these could be discounted because they'd be common between the 3 machines. So most of the variation would be due to the machine if they took a certain measurement protocol. So what they did is they took a 3-day run of the particular part, the most common part that they were producing, and they sampled 10 parts twice a day. There's some evidence that the morning had different performance than the afternoon, so we'll explore that. And so at the end of the day, at the end of 3 days rather, there were a number of measurements collected with the associated machine, day that it was collected, the times collected, which sample it happened to be, and then the resulting diameter of the measured pin. There's also a second data set that measured the throughput on each day for each machine. All right, so let's dive into this. Key thing is keeping in mind what we want to know, which is how variable are each of the machines and their output diameter, and which one has the lowest throughput, and are any of those variabilities something that we could identify as having a source. All right, so make sure we run our first line here, and I've pre-coded here a quick distribution of the value count print statements. So we're going to load in the data. We're going to see the head of the data, so that's here, machine, day, time, samples, and diameters. Again, we don't see much here in just the first 5 rows, but we can see that there are 3 different machines, 1, 2, and 3, each with 60 samples. If we slice it up by days, the data by days, there are 3 days, each with 60 samples. Time, number 1 is morning, number 2 is afternoon, there's 9 of each of those. And then there's 10 samples taken at each of those times of days with certain machines, and so we have a distribution of those. So honestly, the first exploration we're going to want to do is a number of graphical presentations. So what we're going to want, for example, is just to look at the machines, because that's our central focus, and do our cat plot for the machines versus the thicknesses. So be aware everything is in caps, and the other variable called diameter. So that's how we're going to project these. There we go. And we also have to specify the data, which I think was called data up here. Yes, very uninspired. So there we go. We can see that of the 3 machines against diameters, there's a nice tight cluster of machine 2, and it seems like a wider spread on machine 3 than the other 2. Sometimes it's helpful to change this to a box plot because, again, we have a lot of data here. So kind equals box. Okay, and there we can see a little more clearly that there is a wider range for the machine 3 samples than the other ones. It might be helpful as well just to show the mean of this whole thing, so we can add extra lines to this with our regular plotting tools. So we're going to add a horizontal line at the overall mean, just so we can see what that looks like. So the command here is an H line at a certain X or Y value, and we want to plot this at the diameter's mean. Let's see if this works. Perfect. I'm going to make that a red line. There we go, a little more visible. Okay, so a few thoughts right off the top. The mean that's actually the target is 0.125. So, in fact, machine 2 is not hitting on average where it should be hitting. In fact, none of the machines are. They're all a little bit low. So that might be something we would compare afterwards. But we were actually given some variances of plus or minus 0.03 inches, so it might be worthwhile adding a couple of other bars here showing us the actual range of that. So we can plot at, this is again all in inches, so 0.125 plus 0.003, and we'll plot again at minus. We see, okay, that's not as bad. Let's hide the mean here. That's actually the target range we're aiming for. And so machine 1 is safely in there. Most of machine 2, most of machine 3 are actually in that range. So as long as that's the specification and anywhere in there is equally acceptable, then we're good. Both machine 2 and machine 3 seem to have some issues, though, with all the samples being in there. First analysis, machine 1 is looking solid. Machine 2 and 3, maybe some issues there. If our goal is dependability, so least variability, that makes machine 3 bad. If our target is trying to stay closer to 0.125, then maybe machine 2 is bad, or worse of the two. That goes back to our goals for the problem. All right, other variability issues. So if we look at another plot, this time of the days versus the diameters, what we see is that it's actually pretty consistent from day to day, right? So day 1, day 2, day 3, this is pooled across all 3 machines. So looking at those, there's nothing there to really raise any concerns. What we can do though, and this is worth looking at the plotting options for this kind of data set. If you are plotting with categorical data using our cat plot, we've seen these kinds of plots before, that's fine. What we have now though is a mix in, say, day 1. Let's go back to here. Within our day 1, we actually have 3 machines, so it'd be nice to see if those 3 machines are consistent within themselves. So what we're going to do is see how they did this. So they did actually days, interesting, Ys, and they added another parameter here called hue. So that was basically the color difference. So let's try that, where we throw in the machine as the coloring. Well, that's interesting. So now we have on day 1 3 machines, machine 1, 2, and 3. 1, 2, and 3, 1, 2, and 3. Looking at this graph and comparing machine by machine, it looks like, let's look at the easy ones first. Machine 2 seems fairly consistent day to day. Machine 3, again, has high variability, but it's consistent from day to day. If anything, I would argue that maybe machine 1 has a downward trend, a little less constant day by day. Probably not significant given how wide these error bars are, how much range the data itself has, though. So keep in mind, this is a wide variation, and these changes here are relatively small. Again, this is giving us ideas for what kind of statistical tests might be appropriate as a follow-up. But again, helpful for us in terms of breaking this data down in different ways is to use the hue as an extra way to subdivide the data in our plots. Okay, so consistency day to day though, nothing raising red flags there. Let's go to the time of day, and we'll do this in 2 stages. We'll leave the hue off to start with and just see, is the time of day, morning and afternoon, something that's going to be an issue? And just looking at that, the first impulse is to say yes, morning definitely has a wider variability than when the samples were taken in the afternoon, whether there's some kind of startup time, warm-up time for the machines. That's the kind of thing going down to the floor would help decide, but there's definitely a notable difference in the bars here versus the bars here. Compare again within the machines, they tend to be much more consistent in the other plots. Again, because we can, why not break it down by machine as well with an extra comment in there to make it work? This highlights the issue even better. So the size of these boxes between the morning and afternoon for machine 1, pretty comparable. Same for machine 2. Machine 3, though, we see a dramatic reduction in the variability. So again, if variability is what we're trying to minimize, then machine 3 looks like it's eligible for earlier replacement based on this qualitative analysis. Now, just for this thoroughness, because every time we took samples, it's possible that just grabbing them different samples at different times might have had an effect on the distribution. So this is the first sample of each time and day on each machine. This is the second sample for a given time, date, and machine. And we see that generally speaking, those are fairly similar. So there's not like the person who picked up the last sample always picked up a good sample or a bad sample. These are pretty similar. So this is just good procedure to make sure there is no effect from our sampling strategy. Okay, so this leads us to a few areas of investigation that we might want to follow up on. One of them honestly would be more for interest. So the goal here is to identify different variabilities. So one thing that we probably should do is do a little reading on how to test against variabilities. What you'll find is that it's actually reasonably challenging to compare variabilities, standard deviations, with relatively small sample sizes like this. So we end up falling back on graphical analyses just because someone's going to ask, is one machine more precise than the other? I think it makes sense to do a comparison of these three means in production between the machines and just see, are they comparable? Are they consistent amongst themselves? Because our gut instinct is probably not, but it's also good practice for our ANOVA skills just to see if we can do this kind of comparison. So statistical follow-up here, more for interest than to target the goals, variability, and throughput of the case study. Let's compare. There we go. Let's compare the means of the diameter across the three machines. Okay, so we have some tools for this. The sequence again is we want to build a data set that comes from the data, but it's going to be built on the machines and whether they are equal to machine 1. I think these came in as numbers, so I'll do that. And then we want to take the diameter after that. Let's just make sure that works. Perfect. So that's going to give us machine 1, machine 2, machine 3. And we'll just change the values for the machine numbers. That'll all run safely. Then we can do our statistics with the p-value for looking this up. So it's under SciPy stats. And this is 3 different means. So again, what are we actually comparing here? I'm going to grab the graph. It is this graph here and put it side by side. So we are comparing 3 means because we have 3 machines, and that's the F test with one-way data, data 1, data 2, and data 3. So we got our plot here, and of course I forgot the print statement, so we don't see the results. So our p-value is, here we go, with the format. All sorts of horrible syntax issues here. Format of the p-value, bracket, bracket. Perfect. Oh my goodness, okay. P-value is 10 to the minus 12. Again, so the null hypothesis is that all 3 means are the same. We reject that because the p-value is so low. There's a 1 in billions, trillions, quadrillion, lots. 1 in 1 quadrillion, let's say, chance that this data comes from equal mean sources. So if we have faith in our methods, which I think we do based on the other analyses that we did showing things were fairly consistent, matching the experience from the shop floor, then we would reject the null hypothesis. So there's a difference of means. And then again, as extra practice for using the ANOVA and the post-hoc Tukey HSD test, post-hoc Tukey HSD test for which pairs of means are different. Here we have to import another toolbox, grabbing the stats models library, and statistics, and the multi-comparisons, and we're going to import that pairwise Tukey HSD. All right, and a reminder again, you can use the question mark on that to get the help on it, and it'll tell you what the inputs are, and it has this endogenous and groups thing, so just remind yourselves about that. The endogenous is the actual data, so we're going to run our Tukey HSD results. Is going to be from our data endogenous. Sorry, endogenous is the values endogenous, and the data was the diameter, and the groups were defined by the data by machine. That looks pretty good. And we're going to print the result. Okay, there we go. So again, thinking about this plot up above, what we find out is between group 1 and group 2, there's a difference of 0.001902 inches difference. And the key thing is this rejection. Is that difference significant? Yes, we would reject the null hypothesis that says these are the same. We think they're different. From 1 to 3, we also reject it. So even though there's a fairly wide swath in the range of the data here, we do have enough data to distinguish this mean and this mean being actually different from one another, and likewise 2 and 3. These ones come up as being a significant difference as well. All three machines are performing differently. Again, it's not central to this case study that they're performing differently. It's more the variability we want to study. Most of them are falling most of the time in the range that is acceptable for the standards. So this is more an exploration of if there's other concerns that can be brought up during the study, this is some information we can use. It does look like machine 2 is performing lower than the target, so maybe we want to fix that if we're not replacing it. Okay. Well, the summary for this part then is that we have some information, B, from the graphical perspective. From the graphics, which is really all we had to work on, it looks like the machine 3, actually let's go the other way. Machine 1 is okay by pretty much every standard. It had low variability, it had low, and it was quite consistent in terms of being close to the target. All of its output was within the target range. Machine 2 and 3 are the ones that we're looking at more. 3 are more suspect for variability and quality. For variability specifically, though, looks like machine 3 is the worst. Dependence on time, and generally higher variability overall for the diameter. Okay, so that captures, I think, the essential ingredients of what we would look for in this kind of data from the first blush of the variability analysis. We'll then follow up by doing an analysis of the throughput data.